Before we do that, I'll just say a few words about Data Incubator. As you guys may or may not know, we run a fellowship for PhD and master's students who are looking to enter the data science industry. It's a completely free program for fellows to get in, and if you want to know more or you're interested in applying, you can go do that at www.thedataincubator.com. We also have online courses that are targeted towards working professionals, as well as corporate training options if you're in a company and interested in getting training for larger groups. And those are also available at thedataincubator.com. So today, we're going to be doing another installment of our regular webinar on data science in 30 minutes. This is a regular monthly series on data and its role in the world. And we've had past speakers who include Becky Tucker, who's a data scientist at Netflix, Jess Stroth, VP of Data at Quantopian, Holden Corral, and the engineering lead at IBM, who are contributed to Apache Spark, Andreas Moeller, who's a creator and one of the main maintainers of scikit-learn, and a whole host of other folks, including Kirk. And this will be his second appearance today. So finally, before I introduce today's speaker, I want to remind everyone they can pose questions in YouTube on the chat area on the right, and we'll be monitoring those, and we'll pose them to today's speaker as we get towards the end of the broadcast. And you'll also need to be logged in on your Google account to be able to pose those questions. So without further ado, let me introduce you to today's speaker. He's a very well-respected member of the data science community. Dr. Kirk Borne is a data scientist and an astrophysicist. He's a principal data scientist at the Strategic Innovation Group at Booz Allen Hamilton, and has been doing that since 2015. And prior to that, he was a professor of astrophysics and computational science at George Mason University School of Physics, Astronomy, and Computational Sciences. And he'll be talking to us about seeing around corners. So excited to hear what you have in store for us, Kirk.
Great, thank you very much, Michael. I hope you're seeing my face. Hello, everyone out there. I'm going to shift to screen share mode here, so you'll see my slides, I hope. And if we're there, then that's where we'll start. And so before we start here, just to say that at the end of these slides, there will be a link to the place where you can download the slides and view them all you want, all you wish. So if you're viewing this later in a recorded session, then you can go right to the end now if that's what you're doing, and get the slides. Of course, for those who are listening live, you'll have to wait till the end. So as the title says, we're going to use data science to help us to predict the future and to change the future. So one way to think about that is this metaphor of seeing around corners. We're going to talk about how to see around corners. And of course, if you take that metaphor literally, that means if you could actually see what's coming around the bend, and it's not something you would like to see happen, you at least have a forewarning and maybe can do something about it. And so, just the seeing around the corner part, that's what we would call predictive analytics, and doing something about it, trying to optimize the outcome, we would call prescriptive analytics. So we'll be talking about predictive and prescriptive analytics today. So that's where we're going. Data science as the sort of the methodology, using data with a scientific approach to being able to do these things. And you also see right there on the home screen a link to my previous webinar with the Data Incubator, Data Science in 30 Seconds, which is online now. So you can check that out if you're interested in seeing that one. And that particular installment here, I talked a little sort about my career journey, which Michael just mentioned briefly. So I am the principal data scientist at Booz Allen Hamilton, and you can read about some of our things going on there. We're a fairly large group of over 1,000 data scientists today, and we're moving towards having 5,000 data scientists within the next 4 years. So that's a pretty exciting program that we have going on, working across all kinds of different federal agencies and commercial clients. So let's move forward and see where we go here. So I want to start off by just talking about sort of traditional forecasting. Okay, so when we talk about predictive analytics, we're talking about forecasting in some sense. But predictive analytics is not entirely about time series, though this slide is about. For example, predictive analytics might predict which ad a customer will click on an online store. Okay, so that's sort of a predictive model. Or it might be predicting whether a given financial transaction is fraudulent or not fraudulent. In a sense, it's a diagnosis, not so much of a prediction. So all those things are applications of predictive analytics. And the idea is, can we use the data to see a trend or a pattern that helps us to see that coming before it happens? And so in traditional time series forecasting, what normally happens is you do an auto-regressive type of analysis. That is, we look at the pattern, the trends in the data, historical, and then we fit some kind of function or trend line or a combination of a trend line and a function, as you see in these different examples here. And from that, predictor, that red curve, whatever the red curve is, we can say what will happen at some future time. Now, all this completely and totally depends on the fact that we are doing an auto-regressive type of model. And what that means basically is it just looks at what's happened in the past to predict what will happen in the future. So if there's some kind of a tipping point or like a stock market crash, for example, if you haven't seen a stock market crash in the last 10 years and then you use the last 10 years of stock market data to predict the future stock market trends, you will never predict another crash because it's not in the historical training set. So that's sort of the trick here is how we're going to get sort of beyond this auto-regressive problem, which is where we just say we only can predict what we've already seen in the past. But even when you do that, as this slide indicates here, it can have a pretty large error. So in fact, there's a lot of uncertainty in where this time series will go over time. From if you look at the previous 4 or 5 years, then where will it go in the next 2 years? Well, there's a huge amount of uncertainty. If you look at sort of the minimum and the maximum of that error cone, the range of uncertainty in the prediction after 2 years is actually greater than the range of the original data in the preceding 4 years. And so the question is, have we even learned anything if the uncertainty is greater than what we've seen in the past? You might as well just say whatever the value of this time series is today is what is going to be every day for the next 2 years, and you're probably going to be within the error cone. But that's not very informative or useful, but it's still consistent with that range of uncertainty. So what we like to do is sort of move beyond this sort of auto-regressive thing where we just see patterns and we just say, oh, those patterns will just keep on going from today to forever with some error bar on that. So that's not particularly useful. Well, even if you take a physics-based approach, for example, when climate scientists or meteorologists try to predict, for example, in this case, a hurricane, where will this hurricane make landfall? There's even at the most high fidelity physics-based model can have a lot of uncertainty. So this model costs, is a very expensive model on a supercomputer that took hours to run. And if you look at sort of the cone of uncertainty of where that hurricane is going to make landfall, it ranges all the way from the northern coast of South America, all the way up through the Caribbean, Central America, up to the southeastern United States, perhaps even make landfall in South Carolina or North Carolina. So that's a very large range of uncertainty with an extremely high fidelity physics-based model. So prediction is hard to do, as our friend, famous baseball philosopher Yogi Berra once said, it's really tough to make predictions, especially about the future. So yes, that's a pretty valid statement, obviously. But I think what we're trying to accomplish today and in the work that we do is to use the data science approach, that is the data we have and sort of that methodology of finding the pattern in the data through hypothesis testing to see what is the most reliable pattern and trend indicator, and therefore help us to predict the future, but at the same time to understand which variables can impact some change or bring about some change in that outcome and therefore change the future. So both predictive and prescriptive analytics come from these insights from our data. So all of this is consistent with our mission as data scientists. So this is just a simple statement of what we are about in our work is we're trying to discover value, bring about value in the data in our organizations through this data science and machine learning stuff that we know. So if we're not bringing value to our organization from our data, then we've failed. Okay, so we're going to bring about this value, through this discovery process of data science and pattern discovery through machine learning. So I like to call this sort of the easy button for extracting value, and we're going to talk about this in the context of the predictive and prescriptive analytics moment here. So this is just sort of a very simple way of describing it. When people say, well, what are you guys doing? Let's not talk about algorithms. Let's not talk at such a mathematical level, that when someone asks us a general question, what are you doing? Then we don't want them to get lost. So let's talk about it first at sort of the basic level. So initially, we're just talking about, first of all, pattern discovery, pattern detection, just discovering the pattern in our data. And then once we detect and discover patterns, and these patterns might be indicative of things. For example, if you're in healthcare, it might be predictive of certain patient outcomes. If you're in manufacturing, it might be predictive of sort of customer demand or pricing changes. Or if you're in the cybersecurity business, it might be detecting patterns of behavior that might indicate a cyber attack. If you're in the customer business or marketing business, you might be detecting what kind of products customers like to buy. So once you sort of detected these patterns, discovered them, then you want to recognize them again and make decisions based upon that pattern recognition. So you might think of the first step as unsupervised learning, and the second step, pattern recognition, as supervised. Now, before I even get down to the next two bullets on the screen, I should point out that this is very normal for humans to understand, because this is what humans do all the time. Ever since the first human beings came out of the cave tens of thousands of years ago, the very survival of the humans required pattern discovery and pattern detection. For example, they would come out and maybe see an animal or something, or even a wild berry on a tree, and they would have to know whether is this something that if I go after it, it's going to bring me health and life, or if I don't go after it, it's going to be the end of my life. Okay, if it was an animal, do I chase it or will it chase me? Or if it's a wild berry, is this going to be good for me or not good for me? So first of all, detecting the thing and then understanding what it is through this pattern recognition. You've seen this before. You know how to make a decision based upon the pattern. So as data scientists, we have all these data, and we are looking for these patterns and trying to recognize them again. The precursors, warning signs, and signals that help us to diagnose and to predict. But we don't want to do just only that. We want to explore those patterns to see how can we innovate around this. How can we produce data products for better customer experiences or better patient experiences in healthcare, or better outcomes in whatever we're doing. So exploring the data, trying to innovate around whatever patterns we find, and they may be new patterns, completely unexpected patterns, and new things that are very suggestive of innovation steps that we could take. And then once we do that, we really want to exploit all of that stuff, take advantage of it, so to speak, to derive value, take actions in our organization. So it's really all about this easy button here, bringing data to action. So we're doing these algorithms and these data science things and machine learning things, for this purpose of really bringing about decisions, actions, and value to our organizations. So pattern discovery, in some sense, is easy, but pattern exploitation requires more data science. So what I mean by that is this sort of simple little chart here where we have some data points. So those red X's are data points, and there's 3 different panels there, which are different sort of attempts to model those red X's. And so we see the pattern. We see there's a sort of a growth pattern in the red X's, going from left to right. And so we want to take advantage of this and say maybe build some kind of predictive model to understand if we do something at some larger value of X or some lower value of X, we can understand what is likely to be the outcome. Well, the model on the left, which is a straight line, which uses 2 parameters, really doesn't capture the real structure, all of the structure that's in the data. So we're not really fully exploiting the information that's in those data points. There's more information than a linear trend. Whereas if we go to the other extreme on the far right of this diagram, where it says high variance and overfit, on the far left was underfit, clearly. On the far right, we're overfitting. That is, we're trying to fit a high order polynomial, in this case, fourth order polynomial, which means that we have 5 free parameters there. So a 5 parameter fit is overfitting, whereas in the far left 2 parameters is underfitting. And so we're actually fitting every bump and wiggle in the data here and not taking into account that there's some natural variance in the data. So whatever happens sort of at lower values of x or higher values of x in this data plot is probably meaningless, because we've really just over modeled or over interpreted the bumps and wiggles in the data. So it's not very useful. We can't really exploit a pattern if it's bumping and wiggling all over the place. Whereas if you go to the middle one, which we call the Goldilocks solution, that is the one that's just right, not too underfit, not too overfit. It's just right. It captures the trends and patterns in the data, the curvature, the structure of the data, in a generalizable way that we can have a pretty good idea that what's going to happen at lower values or higher values, or even interpolated values between those 5 red data points that we started with. And so we pretty much captured the fundamental pattern in the data, and we also are taking into account the natural variance. And so we want our predictive models to be like this. That is, not to over specify an outcome, not to be too specific, and then of course probably be wrong. Like if you want to predict whether a stock goes up or down so you can invest in it, you don't really need to know to the nearest thousandth of a penny what the stock price will be tomorrow. But if you can sort of generally say it's going to go up a few percent or a couple percent or something like this, that's pretty useful information. So the precision is not the same thing as accuracy. So you might have something precise to 5 decimal points, but it's not accurate to more than 1 digit. So let's be careful. And likewise, we don't want to underfit where we're not really taking advantage and exploiting the real structure. So the goal of machine learning is basically to have a generalizable solution that is using algorithms to discover patterns in order to build classifiers and predictors based off of these patterns. And so the shortest definition of machine learning that I've ever heard is they are algorithms. Machine learning are algorithms that learn from experience. So by experience, I mean observable data. As we move through our universe, move through our lives, or as our machines or sensors or devices move through space and time, they collect data. So that we learn from experience. So algorithms are machine learning, are mathematical algorithms that learn from experience. So we build these generalizable models, and that's the key, generalization, in order to give accurate classifications, not over-specifying or under-specifying. And specifically applying this then to new and previously unseen data. And that's really the whole point of this, is that we can not only use this to explain the data that we already have, but to sort of predict the future and maybe even change the future, which is where we're trying to go. So machine learning has these sort of basic discovery flavors. Okay, so we're discovering clusters or classes in our data. So there's a little diagram in the upper left where we see some data clusters, and as we add more data, maybe we see new data clusters. So we can discover these segments in our data, not only to discover them that they exist, but also what their shapes are and how close they are to one another and how they change as a function of the different parameters, P1, P2, P3. So we learn that the existence of and the rules that constrain the class boundaries in these class discovery or clustering tricks. The second thing we discover there is correlation discovery. That is, there's a relationship between maybe parameter 1 and parameter 3 or something in each one of these clusters. So we learn correlation discovery can become predictive. That, for example, given a value for P1, we can predict what P3 will be depending upon what class or category a particular entity is residing in, data cloud 1, 2, 3, or some other one. We can do predictive analytics on that. So that's predictive power discovery, but there's also prescriptive power discovery, specifically prescriptive power, and data cloud 2 is the best example there, where we see that the correlation between P1 and P3 is shallow for low values of parameter 2, P2, but the correlation strength between P3 and P1 is strong for higher values of P2. So what this tells us is that if P2 is a treatment variable, that is something we have control over, something that we can establish or set in some fashion that we have control over, a treatment variable. If we want to move parameter 3 as our outcome variable to higher values, we know how to with respect to P1, we can move to higher values of P2 and get higher values for P3. So if we want to maximize revenue or maximize customer satisfaction or something like this, we know how to do that because we have this extra dimension of information. So this is how we're going to start getting beyond autoregressive forecasting. Autoregressive would just be like P3 versus P1, and all we know is about the historical trends of P3 versus P1. But with P2 there, with extra data, extra features in our data collection, we say, hey, that relationship between P3 and P1 can change, become steeper for higher values of P2 or shallower for lower values of P2. For example, if we want to reduce the outcome P3 relative to P1, for example, we want to reduce risk or reduce cost or reduce customer churn or something like this, reduce employee attrition, whatever. You know that if you're trying to head in that direction, and you know that P3 outcome is going to go lower for lower values of P1, but how can I achieve lower values of P1? Oh, I see. When I reduce P2, it moves us in a direction where there's that shallower slope. So when we do correlation discovery, we're actually building sort of insights into prediction and prescription. We're actually getting insights for predictive and prescriptive power discovery. And so that's really the clue. That's sort of the hint of where we're going with the rest of the slides here, where the rest of the story here is that we're going to get that insight from multiple dimensions, multiple features in our data set, which is great because when we live in this world of big data, and one of the key characteristics of big data is not just volume. Volume by itself is not particularly useful, but it's the high variety, the many different features that give us these insights. And the last two on this slide, outlier or discovery or anomaly detection, which I like to call surprise discovery or novelty discovery, finding the unexpected, surprising thing, which in that upper left plot, you probably can't see, but on the far left, there's a yellow dot. It's almost invisible with that color, unfortunately. But there's the outlier, finding the unexpected, surprising thing, and maybe that surprising thing is very important. It might be a new emerging customer class, or it might be a scary thing like some anomaly in a jet engine on an aircraft. So surprise discovery is very important. And then the last one on the list requires its own diagram, which is that cute little graph on the bottom left, link discovery or association discovery, as it applies to social network analysis or link analysis or graph analytics. Finding the interesting, perhaps unusual or unexpected associations that link different entities in your organization. And we're going to talk a little bit about that now in a few minutes. Discovering the links and the associations between things, and not necessarily just the direct links, but the ones that are sort of transitive. That is, A is connected to B and B is connected to C, and therefore A is connected transitively through B to C. And then there's examples where that's very important. For example, in money laundering or root cause analysis or marketing attribution, sometimes it goes through an intermediary in order to find that there's a connection from A to C. You have to identify there's an intermediary that's facilitating the transaction A to C. And so that intermediary is not detectable in a transaction database because you only find transactions between A and B or transactions between B and C, but you never actually find a transaction between A and C. So whether it's marketing attribution or root cause analysis or anti-money laundering, the graph model, the network analysis, the link discovery is really critically important. So moving on from there, there's these levels of analytics maturity. And I'll just advance one more button here. So there's actually 5 levels. So we're going from hindsight, that is descriptive analytics, which tells us what happened, where we're just basically reporting historical information. Number 2, which is diagnostic, which is oversight, that is real time, what is happening now, or why is it happening? To the next level, number 3, number 3 is actually the first level of what people call advanced analytics, which is predictive analytics. What will happen? Foresight. So we've gone from hindsight to oversight to foresight. And with prescriptive, we have insight. And that goes back to what I was saying earlier, from the multi-dimensions, more than 2 dimensions, more than just X versus Y or Y versus X. We have other dimensions which give us insight into how things behave And once we understand that, we can sort of prescribe a better outcome. We can prescribe a different outcome. We can optimize what happens. And that comes from the insight. And then sort of the highest level analytics, which can be applied actually at any of the earlier levels. These aren't necessarily sequential, but they're just different levels of sort of cognitiveness, so to speak. So cognitive analytics is when you don't come into the data with a question in mind, but you try to discover the question. What is the question I should be asking when I see this data? What's the right action, the right question, the right insight at the right time, right now? So I got this play on words here. Cognitive analytics is the right sight. So we've gone all the way from hindsight to oversight, to foresight, to insight, now to right sight. What is the right question, right insight, right action, right decision at the right time with the right customer in the right context right now? So it's really just the opposite of descriptive, because in descriptive, we already have the questions in mind and we try to answer them. That's traditional reporting. Whereas in cognitive, we say, well, what are the questions I should be asking when I look at my data? Why is this trend here? Why is this pattern here? Why is there this gap here? What is this outlier doing here? Why is this correlation strength suddenly changing? What is this emerging behavior in my data? That's cognitive. That's what the human aspect of machine learning, sort of replicating what the human would do, which is looking at the data and saying, what is that? Why is that? That's where we want to get to. So the real difference between predictive and prescriptive is, in simplest terms, is a long mathematical statement there about given the historical data, we can predict the future. That's predictive. And then, given how the data, the relationships between the data versus the independent variable, we can sort of prescribe a better outcome. But another way of saying that is on the left, given X, find Y. Given X, find Y. That's predictive. Prescriptive said, well, I want a different outcome. I want a better outcome. So that's given Y, find X. So those are exact opposites. So predictive and prescriptive actually are exact opposites to analytics. Given Y, find X, it basically says, I want a better outcome. I want higher revenue or more customer satisfaction or lower risk or lower employee attrition. So what conditions must I set in my organization to achieve that better outcome? And that comes, again, from having the insight from many pieces of contextual data. And it's not just Y versus time. It's not just an autoregressive univariate function. It's multivariate, many variables. So a famous philosopher described predictive analytics. Confucius says, study your past to know your future. So that's basic, a simplest possible statement of what training data does for you. And Confucius actually said this. Study your past to know your future. So that's a perfect description of predictive analytics. And for prescriptive analytics, our good friend, baseball philosopher Yogi Berra, once again, we've already quoted him a couple times earlier. He said, the future ain't what it used to be. So instead of just predicting an outcome that we may not like, we may want to change it, optimize, get a better outcome. And that's what prescriptive is all about. And so the future ain't what it used to be. So getting right into predictive now. So predictive analytics is probably one of the most significant applications of machine learning. That is these algorithms that learn from experience. That is, it learns patterns from prior data. And when we look at sort of analytics in a general way, that is, what are the applications of machine learning and AI and business strategy discussions? I found this chart, and all the little red boxes in this chart I've added the red boxes. And pretty much every one of those things in a red box corresponds to some kind of prediction or diagnosis or optimization, a recommendation or optimization or forecasting or credit scoring. Credit scoring is nothing more than sort of predicting whether a customer is going to default on a loan or not. That's a predictive model. So pretty, an overwhelming majority of these business applications are predictive and or prescriptive analytics. So it's one of the hottest things going in the analytics world. So let's talk a little bit about these advances, and I'll give a few examples. That will be the sort of the rest of the presentation. Just a few short examples here. And there's a cute little cartoon here about the cats are using predictive analytics, and they say, according to our predictive analytics solution, the mouse should be exiting from this hole in 3, 2, 1. Well, the mouse did exit. It just exited a different hole. So these cats needed to see around corners, okay? That is to say, they were pretty close to what was going to be right, but they just didn't get the right location, but they did get the right time. And so that's almost a figurative and a literal explanation of seeing helping predictive analytics helping us to see around corners. So let's go into these examples, and these will go by kind of quickly. But again, like I said, the slides will be available later, and you can go back and look at them more slowly because I might go through them a bit quickly here. But the first one is cognitive analytics. And again, coming back to our famous baseball philosopher one more time, Yogi Berra said, you can see a lot just by looking. And so this, the example I want to give is not related to data science or analytics exactly, but it has a good analogy to analytics. And so you'll hopefully see that analogy once I sort of tell you the story. So the story goes back actually to the 1950s, a Formula One race, which I believe was in Italy. Now this photograph was a much more recent photograph from London, 2017. So the picture here is just for your, for you to look at while I'm telling you this story about a Formula One race that happened about 60 years ago.
You can even see the underground signs in the corner.
Yes, there you go. So it is definitely London. So, but anyway, so about 60 years ago, there was this Formula One race. And then before I tell you the story, make sure you look at the top of the slide here. We're talking about Yogi Berra's quote, "You can see a lot by just looking." Or my subtitle is, "You can actually see around corners by just looking." Because you can be cognitive, contextual, insightful, and forecastful if you do that. So all those words mean what I'm about to say. So in this race about 60 years ago, as you know, probably, most of these Formula One races go through major cities on the city streets. And so there's all these sharp turns around the city. And the cars are, race down the straightaway, past the crowd, and then they turn around a sharp corner, and they have to, slow down and then speed up around that sharp corner, and so forth. So it's not like a big oval like an Indianapolis 500 type of race where you can, you're just going around and around the oval, and you can see far, far ahead what's going on. In this case, you really can't see very far ahead. So how can you see around corners? Well, what happened in this particular race was around one of these sharp corners, there was a crash. One car crashed into another. But since the drivers can't see around corners, the next car will come around the corner fast, take the corner, come around, and crash again. Couldn't see the crash ahead of it, so it would run into those cars. And then another car, same thing. Another car, the same thing. So there was a multiple car crash. All these racers came around this blind corner since they were not able to see around the corner and crashed. But another driver took the corner more slowly and more widely and completely avoided the crash and ended up winning the race. And so at the end of the race, he was being congratulated for his brilliant skills as a driver, how he avoided the crash, and how wonderful he was and fantastic. He won the race because of his brilliant skills. And the driver is just shaking his head. He's just, no. That's not what happened. So they said, well, what do you mean that's not what happened? And he said, I just knew something was not right. And they said, what do you mean? He said, well, I didn't really understand it then, but I can understand now. Just it was instinctive. As I was going down that straightaway before the curve in the road, I noticed the crowd. I mean, in my subconscious, I realized that the crowd was not looking at me, which they should have been. Here I am whizzing past them very fast. They should have been watching me go past. But instead, they were looking down the street. They were looking down around the corner. So therefore, he just instinctively knew something had to be wrong, but the crowd wasn't looking at me. So I decided to take it a little bit more slowly and a little bit more widely around that corner just to be careful. And sure enough, able to avoid the crash. So that's how the driver won the race. Now, how does that apply to analytics? Well, it applies to analytics because in this metaphor here that I'm trying to portray, the crowd is your other data sources. They're sensors. There are other sensors about what's going on in the environment. And those sensors are pointing to some other event that your main sensor, which is your eyeballs, that is the driver in the car. So if you're looking at just a time series and only the time series, for example, a stock market price, and you only look at sort of the road in front of you, that is and the road behind you, that is just looking at the price of that stock, you may miss something that's about to happen, a tipping point, or an emerging event or a crash or something, whereas there's all these other indicators, all these other parameters, whether it's social media or the news or policy or other financial markets. There's other sensors which are giving you an indicator that something is not right coming up around the bend. And so being cognitive, that is being aware of all these contextual factors and saying, well, gee, why is that? Why is everyone looking at something else? Why is all the data pointing to some other thing? Why are all the early warning signs indicating something is about to happen, even though my data stream doesn't indicate that? So you're being cognitive, contextual from those, and from those insights, you can now become better at forecasting that something is around the corner and take appropriate action. So one could have said, just taking the data alone, we could predict that this car was going to crash. Well, it didn't. It didn't crash. So not only was it predictive analytics at work here, there was prescriptive, that is, picking a different course, a different path around that corner in order to avoid the crash. Now, of course, if you asked that driver 60 years ago to explain what he did in terms of analytics, obviously this is not what he would have said. But I'm extrapolating from what happened then to what we would do nowadays, which is look at our other sensor data and grab that context and see if there's sort of early warning signs in the data. And that context gives us some way to see around the corners, just like those people who were looking down the street and not at the driver passing by was indicative that something different was going on than normal. So that's number one in my example of seeing around corners, literally in that case, around the corner of the Formula One race. So that was cognitive. So the second one on my list here is associations. And what do I mean by that? I'm starting with textbook stuff, and then I'm going to move to something that's not in the textbook. So bear with me a second here. So association discovery in all the textbooks, and sort of there's the very traditional example that's been in textbooks for years, 20 or more years. This example that said that when men go to the store to buy diapers, they tend to buy beer at the same time. So in a sense, it's predictive, right? Because the diaper purchase does not by itself imply a beer purchase, but when the men go to the store to buy the diaper, they do tend to buy beer at the same time. So in a sense, that's sort of the early example of a recommender engine, knowing that a purchase of one item leads to the purchase of a different item. And so we know that Amazon has exploited this, Netflix has exploited this. Customers who viewed this movie or recommended this movie or gave it such and such a rating to this movie would give such a rating to this other movie. So based upon your viewing patterns and other customers' similar viewing patterns, Netflix can do a pretty good example of predicting whether you would like or dislike a particular movie. Similarly, with a lot of other websites, e-commerce stores, they all have recommenders now. So that's finding those interesting associations. So one example of this was back in the early 2000s, about 14 years ago. Walmart looked at their transaction logs, the customer purchases after a hurricane hit Florida, in order to see what customers really, really like to buy prior to the arrival of a hurricane. And this was actually quite valuable because there was actually 2 other hurricanes predicted to make landfall on Florida that year. And in fact, they did. The hurricanes did come. And so Walmart said, well, if those hurricanes are coming, what is it that people really want to buy prior to a hurricane? And since they had just one hurricane that just passed, they could look at all those data from millions and millions of customer purchases. And they discovered there was one particular product that sold 7 times compared to the normal shopping day. There was a 700% lift, as you would say in association mining. It's a huge lift, 700% lift. If you can find maybe 2 to 3 or 4% lift in a marketing campaign, that sometimes is enormous, but 700% is really enormous. They discovered that there was one particular product that customers really, really wanted to buy prior to a hurricane compared to normal shopping days. And it's not water, it's not plywood, it's not flashlight batteries or toilet paper or any of those kind of things you might think of, like electric generators or whatever. Turns out the answer is strawberry Pop-Tarts.
Interesting.
Indeed. Yes, indeed. And there's links on this slide, and then when you download the slides, you can actually click on these and follow the story about that. And and you can imagine a scoring model as a data scientist why this might be true, because Pop-Tarts, they come in individually wrapped packages. They have long shelf life. They don't need to be refrigerated. They don't need to be cooked. They're a comfort food. They're a snack food. Children like them. Adults like them. They contain fruit. Maybe. Anyway, so there's lots of reasons why a product like this might be popping to the top of people's shopping list prior to a hurricane. But that's not my primary example. My colleagues at George Mason University actually took this same market basket analysis that's applied in shopping cart analysis to hurricane analysis. And not the kind of hurricane analysis I just talked about, that is, what will people buy? They said, let's look at hurricanes when they're still far out over the ocean, historical hurricanes, and we'll look at different hurricanes of different strengths. Like when they make landfall, they could be the strongest hurricane, which is hurricane level 5, or less strong, 4, 3, 2, 1, or just a tropical storm. And they basically created what they called market baskets, but they're not markets, obviously. Market baskets of hurricane 5, 4, 3, 2, 1 tropical storms. And then in those baskets where they had those hurricanes, historical hurricanes, with which they knew what the landfall strength, wind strength was, they said, okay, what were the physical properties of this hurricane while it was still far out over the ocean, like the wind speed or the shear or the pressure drop or the precipitation level or the sea surface temperature or the cloud cover, all kinds of different parameters. And they compared those parameters, they put all those parameters together in those baskets, and they said, here are the parameters that most strongly associate with hurricane 5, strength 5, 4, 3, 2, 1, or tropical storm. And at the end of the day, they actually discovered an association set of rules, which had higher predictive accuracy, predicting what the hurricane landfall strength would be, better accuracy than the prediction from the National Hurricane Center, which has a very high performance computing, high high fidelity physics model simulation, and this does better than that. Now, what this does not do, it does not say where the hurricane will make landfall. So still that National Hurricane Center model is still extremely important, of course. No one's saying that it's not. But in terms of predicting what the wind speed would be when that hurricane hits land, no matter where it might hit land, this particular association rule discovery model is better. And so in a sense, you can't necessarily say, and the National Hurricane Center will always tell you this, they can't necessarily tell you what the hurricane strength will be when it hits landfall. So a better predictor model, that is how to see around corners, so to speak, even though the hurricane's still far out over the ocean, you can get a better predictor out of doing this association analysis, which is quite unexpected and quite successful, actually. Quite a few research papers were written on this particular application. Pretty interesting stuff. So taking something that was used in basic market basket analysis and applying it in a very unexpected way. Number 3 on my list here, so we see we're moving along here, is graph. So graph models, I totally love graph models because the natural data structure of the world is not rows and columns, it's not spreadsheets, not Excel spreadsheets, but it's a graph because it's all about entities and the relationships between them. Whether it's customers or products or diseases or social networks or anything. It's about how things relate to one another. It's the relationships between things. And so I like to paraphrase our friend William Shakespeare, who said, all the world is a graph. Well, actually, he didn't say that. He said all the world is a stage. But, considering that all of his plays were about entities and their relationships, that is, people and their relationships, I think he was probably thinking about a graph, actually. Didn't call it that. But maybe he was thinking about that, because I think if he was living today, maybe he would say stage, all the world's a stage. Maybe that stage is an acronym for Spatial Temporal Analytics Graph Engine. So anyway, so once you realize sort of how things are related and connected, you can start building predictive models. And so just a little bit of the power of the graph on this slide, and there's a lot more words here that I have time to go through. But again, it's that relationship thing I told you about earlier, where 1 might be connected to 2 and 2 might be connected to 3, but 1 and 3 are never connected anywhere in the graph. So if you had a regular transactional database, rows and columns, you would never see a 1 to 3 connection. But with a graph, you can instantly see that it goes through this intermediary too. So this is an illustration of money laundering in this particular. So the black hat entities 1 and 3 never actually exchange money. They go through a white hat entity, that is someone who doesn't raise any red flags to the authorities and consequently get away with money laundering. Okay, that's sort of a negative example, but a positive examples of the same uses the same graph model include, as I already mentioned earlier, marketing attribution, root cause analysis, even medical research discoveries. So there's a field of research called literature-based discovery, LBD, literature-based discovery. So if you look that up, it's very similar to this, where it just looks across the network of references in papers, and specifically the semantic concepts within the research paper. So the actual concepts that are being discussed in the research papers, and find papers that are talking about those concepts, and then find other papers that are connected to those papers, and then other papers connected to those papers. Then after a while, you have a graph, and the links in the chain are such that maybe where you started has no correlation at all with where you ended. So people have actually discovered treatments for diseases just by doing this type of discovery analysis, graph analysis, link analysis on the medical research journals. So the treatments, the cures, maybe not necessarily cures, but treatments for some diseases have been discovered simply by mining the semantic medical research graph. And so there's all kinds of really wonderful applications of graphs, and one of those is journey mapping. So it's looking at, for example, customer journey, but this can also apply to patient journey in healthcare. It can apply to employee journey in a human resources application. It can also apply to a product journey, for example, in a manufacturing plant or anything like that. So what are the touch points in the graph where things change, which causes an action or a reaction? Customer leaves, customer stays, customer is unhappy, customer called the customer care center, customer left a favorable review on social media, maybe customer left an unfavorable review on social media. So looking at all the interactions in that graph, you can and then you start finding other customers who start having those same type of interactions. You can be very predictive as to what that other customer, what the outcome is going to be, or the patient, or the employee, or the product. So graph models capture that enriched multi-dimensional pattern in the data. So that's very forecastable. There's no single time series running through this. It's a multi-dimensional graph. It really is not single variate autoregressive time series at all. I mean, it's completely different from that. And so this graph analytics is very powerful for predicting outcomes. Unbelievable. And the last one I want to mention before we finish here is clustering analysis. So this goes back to a story back in my NASA days where I was asked to give a presentation to the summer interns. This was about 14 years ago, about data mining and machine learning. And I said I picked something that was relatively easy to, that was approachable, because the summer interns had many different backgrounds, different levels of math and science and engineering. Even some of the interns had none of that background. They were basically there in other capacities serving NASA in different functions. And so I said, well, clustering is very straightforward. We all understand clustering, even as children. We cluster things by our toys, by their shape and by their color, even by their function. For example, we know we can play ball with something spherical, but we can't build a castle out of spherical things. But we can build castles out of blocks. But we don't want to play ball with a block. So children are already good at this. So clustering is a natural thing. And then what we do in data science is we start analyzing our data based upon our different features. But because this is an unsupervised approach to the data, that is an unsupervised machine learning methodology, there's not necessarily any one right answer. And so as we see in this case, we have some colored geometric shapes on the left. And if we cluster them by color, we get one set of clusters. If we cluster them by shape, we get a completely different set of clusters. And this is true in general with any data set that we have, whether it's customers or patients or employees or products or recommender engines or anything we have. Depending upon the features we cluster on, we can end up with completely different clusters. And so at the end of the day, because it's unsupervised, there's really no prior knowledge about any of this. There's no prior knowledge of what the right number of clusters is, even what the clusters mean at the end of the day. Different clusters are possible from different data sets, as shown here. Different clusters are even possible depending upon what similarity metric we use. What do we mean by two things are similar? How we define similarity changes what the clusters will look like. So I was talking about this in this presentation at NASA years ago. explaining clustering and how data scientists do it and some of our challenges. And so then I said, well, how do you know if clusters are good enough? And I say, well, you know they're good enough if the clusters are compact relative to their separation. So if the clusters have strong overlap, they're not really very true segments. They're not very distinguished from one another. It's not really a true segment. You really want to find clusters that are compact, segments that are compact relative to their separation. So if the clusters are well separated from one another, and that sort of the within cluster errors are small, that is, there's a sort of low variance from within, but also that you don't want too many clusters. I mean, it's sort of meaningless to say every point is in its own cluster, even though there is an application called personalization or hyper-personalization in marketing, where they talk about seg1 clustering, that is segment of one. But in general, that's not what I'm talking about. I'm just talking about what's good clusters. You don't want to have too many. So that would be overfitting, as we talked about earlier. And you don't want to have too few. That says, if you say everything is one cluster, like all your customers are exactly the same, so let's recommend the same product to every single customer. Well, you obviously know that's not a good suggestion either. So underfitting, overfitting is still a problem. So how do you know? So since I had a pretty varied audience for that presentation at NASA, some who had math literacy, high levels of math literacy, mathematics majors and engineering students and science students, and there were others who did not have that. I said, okay, I don't want to keep everything general, so I did put some mathematics in. As you see here, I included a description of one of these techniques, which is called the DBI, the Davies-Bouldin Index. And I don't need to worry about the details of that formula right there, which you can click on the links later on and you can read more about it. But basically, it's a way of just measuring sort of the within cluster separation versus the between cluster separation. In other words, intra-cluster versus inter-cluster separations. And so this is a way of just summarizing all your data points for different types of clustering. You can assume different types of clusters, the numbers, the features, the distance metrics, all those things that can be variable, and find the most compact set of clusters. Then when you found the minimum value of this index DBI, then you found the best or the optimal set of clusters that you could possibly find. So it's really an iterative process. So this is the data science side of this. It's iterative. You have a hypothesis of what the number of clusters are, what the correct features are to work on, and maybe the correct similarity metric to sort of measure similarity between things. And then you measure DBI. And then you iterate on that. You test other values of the number of clusters, the features that you want to use, and so forth. And you keep doing this multiple times, iterating and iterating and iterating on different values of all these things until you find a minimum in this function. Now, of course, you have to stop at some point, probably because you run out of resources or run out of time or your boss runs out of patience. Anyway, so it turns out, so I gave this presentation to the interns, and I didn't think much about it. Of course, there was a lot more to it than just these two slides, but I gave a lot of this information. And that was the end of it. And 2 weeks later, I got a call from one of the NASA chief scientists who works in the field of space weather, who basically analyzes data that's observed the sun. And so when we see solar flares and storms on the sun and solar prominences and all these exotic events on the sun, a lot of times those events lead to highly energetic particles being hurled toward Earth, leading to power outages and satellite communication breakdown, beautiful things like northern lights, but also can cause cancer in airline flight crews who fly over the poles during their flight. So they want to build a better predictive model of when we see things on the sun, when will things happen on the Earth. And this scientist had spent decades working on this problem. He called me to his office one day, sort of 2 weeks after I did that intern presentation, and he said, hey, I got this guy here I want to talk to you about. So I go to his office, and the summer intern had actually solved the problem using clustering analysis that the NASA chief scientist had worked 25 years trying to solve with the high fidelity physics model. So does that sound familiar? We have the National Hurricane Center with the very high fidelity physics model, and we have the market basket analysis doing better at predicting the hurricane anticipation. Well, in this case, what the young man did is he did this clustering analysis, and the clever thing was he was trying to cluster solar parameters with Earth parameters. That is, when these satellites measure things on the sun, like the magnetic field strength and the X-ray flux and things like that. And then he measures things from the satellites. I mean, all these satellite data are available publicly and openly. Things that he can measure at Earth, like what is the electron temperature, what is the flow particle density and the electron density, so to speak, in the solar wind at passing Earth. What is the speed and all these kind of parameters. And then he looks for the tightest possible correlation between solar parameters and Earth parameters to make this discovery. Well, so that was fine, but the real clever thing he did was he time shifted it, because he knows that when something happens on the sun, it takes a few hours before anything appears at Earth. So he said, well, I don't know what the right time delay is. So he did the clustering at 0 hours, 1, 2, 3, 4, all up to 12-hour time shift. So he shifted the solar data with respect to the Earth data by these different time shifts. And what he was doing was measuring the compactness of these clusters to see how compactly correlated the sun and Earth parameters were at these different time shifts, looking for the minimum. And then he found that minimum in sort of the 2 to 3 hour time range in very specific solar and Earth parameters, which was the discovery that the NASA chief scientist had spent 25 years trying to make. And the summer intern was able to do it in a couple weeks. Pretty interesting story, actually, and there's more to the story that I didn't have time to spare today, but just to give you a little hint.
The power of machine learning and data science that can often be more powerful than kind of a lot of traditional methods.
Exactly. So what I like to say, people, how data science might differ from traditional science or computation. I mean, it is still science. I wouldn't want to say that it's not science. It is science. But how it differs is that the data itself is the model. That is, the data carries with it the information and knowledge. You just need to decode it. So all that information about how, in this particular case, there's a causal event and there's an outcome event and there's a time shift, right? That applies to marketing, it applies to healthcare, it applies to customers and employees and products and manufacturing and machines. It applies everywhere. So when you see some event and there's some outcome that happens later on, you can look at this, in this example, clustering is an example, association analysis is another example, the graph analytics is another example. You can use all these examples with time shifts and say, can we find when we have to have the tightest, most accurate correlation and prediction between cause and outcome, and what is the time shift that gives us the most optimal prediction? And in this case, it was the 2 to 3 hour time shift. So this can apply to any number of applications. I'm not here to give a physics lesson today, even though my examples seem to be coming from physics. But the idea is you can apply this to any data set. And that was the real clever insight the student had, was to do the time shift and then to do the analysis with the time shift.
And I know that we're sort of running short on time here. Yep. I did want to pose to you a few questions from the audience.
Yeah, let me just finish, and then I'm literally there, and then you can pose those. I just wanted to say that, and in summary, what we need is contextual data, and I like to just say the Internet of Things is one way that we're going to get data from many different sensors. So think about that race car driver. He had extra sensors, that is the audience watching him. So these sensors give us contextual data. So I like to refer to the Internet of Things as the Internet of Context. So it's moving as far beyond autoregressive and univariate forecasting to this rich contextual forecasting. So sometimes you might want to call this even forecasting as a service, that as all these different sensors give us information about what's coming around the corner. And that really truly is my last slide. And there's the link where people can get the slides, and I'm ready for questions.
Oh, great. So yeah, I think that there's maybe I have room for 1 or 2 questions. So one question folks have, or one cluster of questions that folks have, seem to be around the kind of, let's call them mathematical, statistical, or machine learning topics they should be learning, right? Statistics, optimization, machine learning. What would you say they should be doing?
Well, it depends on your application. So that's a pretty broad question. I mean, certainly a lot of value creation, going back to what I said very early on, the role of data scientists is to bring value, create value out of all the data assets in an organization, right? And one of the greatest value creators is predictive analytics. Okay, that comes by, again, knowing how to find the pattern and exploit the pattern. And so machine learning is part of that. So definitely go there. But once you have all these extra dimensions of information, you can sort of see how those predictions change as a function of these different other variables. And if any of those other variables are treatments, that is, things that you can change, you have control over, they're not totally independent variables, they're things that you actually have then you can move the outcome to a better, more optimal outcome. So once you start exploiting and exploring the data, you can start becoming predictive and prescriptive. And that by doing so, you become quite valuable to your organization.
Got it. And then another question. So a lot of companies are trying to claim that they're doing machine learning, but we kind of scratch the surface. Maybe what they're doing is handcrafted rules or something kind of very, very simple. And I guess the questioner wants to ask, how do you separate out the people who are really doing deep, let's say, data science versus the ones who are more superficial in their application of machine learning or AI?
Well, that's actually a pretty good question. I think the first thing I would do is just how many data sets are you looking at? And I don't mean necessarily volume. I think volume is highly overrated. I mean, the more dimensions you have, the more insight you get from your data. So you can have a relatively low volume of data, but if you're not looking at all the different features, then in a sense you're sort of like doing sort of traditional analysis. And that the sort of the metaphor I like to use for that is the blind men feeling the elephant. If you're familiar with that one, where the different blind men, or they have blindfolds on. One of them is feeling the tail, one is feeling the trunk, one is feeling the leg, one is feeling the body of the elephant, and they all have a completely different description of this thing. But until they take the blindfolds off, they don't really get the full understanding of this complex thing and what it's capable of and where it's likely to go. And so in a sense, we're talking about silo smashing here, right? If every line of business has its own data and is not sharing it across the enterprise, you're not going to get that full 360 view of the customer or the employee or the organization or the enterprise. So I'd say no matter what the volume of your data is, and no matter how sophisticated your algorithm is, if you're not combining multiple data sets or lots of features within even a single data set, and of course that's going to require sort of multi-dimensional analysis and feature engineering and all kinds of stuff, which therefore tells me you are an advanced data scientist. I mean, you can do advanced data science just with regression if you're doing it smartly over many different dimensions of data. So I'm not necessarily looking for someone who's using TensorFlow or some high performance computing cloud with deep learning algorithms. Yes, that would be fantastic, but not everybody's going to be doing that. But if you're combining many different data sets and sort of, in a sense, you're sort of sneaking around the data to see what the pattern is in the data, because two clusters can be projected on top of one another in low dimensions. But as soon as you look at those clusters from high dimensions, in a sense, sort of turning your head and looking at it from the other side, all of a sudden you see there's two clusters. So until you start looking at those higher dimensions, you can start separating different predictions one from another. You can separate different diagnoses in a healthcare situation, but the symptoms might be the same for two completely different things. I just published a blog yesterday on this topic, where a patient comes to the doctor and they say, I have a headache. Well, that headache might be a symptom of sleep apnea, or might be a symptom of pregnancy. It might be a symptom of a brain tumor. Well, there's some pretty different diagnoses and treatments needed for each of those cases. And so there's a lot of overlap in the treatment space from one single symptom. So what do doctors will do in that case? They'll ask for more lab results. They'll ask you more questions. And that, in a way, is actually, by asking more questions and getting more lab results, that's actually looking into the hyperdimensionality of that illness. And so if data scientists start looking at the hyperdimensional aspects of their data, then I really truly believe that they're sophisticated advanced data scientists.
So I want to thank you for taking the time to speak. I want to thank the audience for also joining us. We had over 1,300 people sign up for this. And it's
fantastic.
A lot of interest in hearing you speak, Kirk.
Well, thank you, Michael, and thank you, Data Incubator, for all that you do.
And so I hope the members of the audience enjoyed this as much as we certainly have. For those of you who want to learn more about the Data Incubator, including our free data science fellowship for PhDs and master students, our online courses that are more geared towards working professionals, or our corporate training, you can learn more by going to our website at www.thedataincubator.com. So thank you so much for taking the time. and hope to see you again in a year or two on another installation of Data Science in 30 Minutes, Kirk.
Thank you very much, and I'll look forward to more of yours coming soon.
Cheers.
Au revoir.